Going further in the first part, we covered the front end part, how to make how to fix the circuit values, how to decide the various large signals, small signals like VDS, ID, W, L, GM, slew rate, SMRR, and things like that. Now this is the design flow. So we start with the design specifications are given, then finalize the architecture, and then do the schematic entry and complete the circuit. And if the specifications are met at the front end level, at the circuit level, then we will go for the physical implementation. Physical implementation is how the devices or how the various elements will be fabricated, how they will look physically, which is also known as the layout. And after doing the layout, we have to verify that whatever layout we have done, it is matching as per the circuit. And there because of interconnects, there will be some parasitic, so we have to calculate those parasitic and effects, and then again we have to simulate the circuit, taking into consideration the various RLC parasitics, and see whether the specifications are meeting or not. If the specifications are not meeting, then either you change the layout, or you may have to change the architecture completely also. And if the spec is meeting, then finally you go for the chip finishing. So there are many things in the chip finishing also, like putting of the IO pad rings and dummy fails, corner fails, and then finally a GDS is released. So what is layout? Layout is creating geometries. Earlier we saw that W and L are the two geometries of any passive or an active component. So we have to define those and we have to create those. So from the circuit from the layout, we will get these various polygons, and these polygons, they are used in generating the masks, which is in a format known as GDS, and all these masks, they are used in fabrication of the device. So this was the circuit which we discussed earlier. This is an op-amp, symbol is given, and this is how it looks if we do the physical implementation. So here, this is a VDD top, and this is VSS, and you can see here now this is the VN. So this is one transistor here, VN, and this is another transistor which is a differential pair. So this one and this one is forming a differential pair, and we are taking the output from here, V out, and this is a VB. This is the biasing part of these transistors. So this shows, you can see various colors and various polygons, and these polygons, they represent some layer. So we will see these things. So this is in a typical simplified CMOS process. It's a single well process. So there will be some color like this color for a P well, green for N well, and there will be, first we have to define the wells. In the wells we have to define the active area and field area. So these will be like in this is a mask. If it's a positive mask, wherever this square polygon is coming, there P well will be formed. So P well, in the sense, in this particular side, the boron will be implanted, and that area will become a P. And within that area, if this is P, I will make N transistors here. So this whole thing is P. The rest of the area, which is white in color, it is unchanged. So in this area, some portion I will define active area, which is green in this shade. So you can see this is smaller than this. So there will be some active area, and in this active area we will define the transistor. Active area is the area where components will be made. Rest of the area is a field area, and this is the poly you can see here. So this is the polyline polysilicon, and below this will be an GOX, gate oxide, and then both sides will be diffusion masks, and diffusions are not shown here, but how you can see you can take this line, put on this here exactly. So other side of this line will be a source drain diffusion. So this is how active area, on top of it is a gate mask. So this is how it comes, and then finally you have to make contacts. You can see these are the contact. This one dot you are seeing, it is on this line, it's a gate contact. And as I told you here, this transistor, you see this is a diffusion. The definition of transistor is a poly which will cut the diffusion. That is a transistor. So diffusion will cut. So this polyline is cutting the diffusion, so it becomes a transistor, and you have to make contacts as we are making contacts here. And then finally by metal you have to connect these. And if there are two metal, you take a via and go to the second metal and things like that. This is a very simple explanation. If this is a wafer, this is a mask which is a quartz plate, and there is a quartz glass and a chrome pattern here. This was the area through which the light will pass, and it will, you have defined this area. Now you have defined this geometry. This is a photoresist. Depending on positive or negative photoresist, one will dissolve, and you have defined this geometry. If you want to like do some boron implant, then after that you do an implant. What will happen is this area is open, boron will go here, and this area photoresist is there, and the boron atom will be struck in this photoresist only. They will not go in the wafers, but here, since this path is open, they will directly go in this. So this is how it fabrication is done. After the end of the fabrication, this is a cross section which you are seeing. This is a P silicon, this is a P well, this is an N well. So let's take this N well. These are this is a P well. So these are N diffusion. This one, this is N diffusion. This is N diffusion. This is contact. Okay, this brownish is contact, and this blue color is a salicide to improve the resistivity. This thing is a gate. This one, this color, gate oxide. This is poly. This one, yellowish. This is poly. This is the contact. Brown is the contact. Again, this is a salicide. This is a via. So it's going top on top of. So this is one transistor. This is another transistor. This is Fox. This particular thing. This one, which you are saying. This also is an oxide, and this particular thing separates these two things. You can see here. So this is another transistor here. This is another. So this is the separation. So similarly, this is another transistor. So this bluish this can be cobalt salicide also, or a titanium salicide also. So there are 2-3 things, metals which can be used. So in a modern, they have more than 200 processing steps, and this is a 3D view of a transistor. So this is a bulk, this is length, this is W, this is gate. Now from the top, if you see, this is source. You will make contact here, here, here. Drain, you will make contact here, here, here. But this gate, normally we don't make contact here on this. Since below the gate is the this is a reddish color, is a poly, and below this will be a gate oxide. So we don't want to harm in any way this gate oxide. So normally outside this square, this area is a active area, and outside this area is there will be a field oxide or a shallow trench isolation, which is just for isolating. So this gate will run over that isolation, and there we will make contact. So this you can see here. This is a cross section, Okay, and these N and PMOS for a CMOS both have to sit together. So this is Fox. Now you see this is a P substrate. This is a P. So you have taken a P contact, P plus. You have taken a contact. These two small squares, they are a contact. In this area, there will be active region. Whole thing. There will be active greenish, and then this active region will be cut by this reddish, which is a poly line. Then it will become a transistor, and then you do the implants and both sides, and then you take these contacts. So you are taking contact source drain here, 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 and as I told you, this poly is going on the field region also. This area, this is field, so you will take contact here. So this same way here, except there's a piece of thread here. It's an N well, so you have an L well. So this is an N well. On the top view, this is cross section. So you have an N well here. This one. This is an N well. Okay, so this is W. This is L. Okay, so this now, what do we mean by design rules? So the design rules, you see the thicknesses of the layers. This is the cross section. In the cross section, there are various layers, various thicknesses. That is a part of the transistor definition. This is a process that designer cannot change. On the top, you have these polygons. You can alter the shape of all these polygons. That is with you, but there are certain rules like what should be the minimum L, what is the contact size, what is the one contact to contact distance, like what is this contact to this distance, what is this edge to this distance, like this. So there are various rules you have to do this, and these rules are based on, because if you make two lines so narrow in fabrication, it will not be possible. There can be either shorts or opens. So keeping in the fabrication manufacturing process in mind, these rules are defined. So these are known as the design rules. Okay, so these are the all design rules can be categorized in four different, like what is the minimum width, what is the minimum space, what is the extension, what is the overlap, what is the extension. If some layer is coming over the top of that layer, so there it has to extend so that there is a proper connectivity between the two layers. So we will see some of these. You can see here it's a 2 is the width. You cannot have a like in a 180, you cannot have a width which is less than 180. Then there is a separation which is known as a spacing rule. So two polylines can be separated by this minimum of the maximum can be more, but you cannot separate these two lines. And then this is a well. Then this distance where 2 is written, that is a minimum width, right? Minimum spacing to well. And this is also minimum spacing within the well and outside the well, which is wall. So these are the spacing rules, and these are the extension rule. You can see if you are making this contact, if you make this contact towards this side, at almost at the edge, what may happen is during fabrication, this edge might shift slightly here. So the contact will not be a proper contact. Your contact resistance will be very high. So that is the reason you have to make the centered contact so that there is sufficient enclosure on all these sides. So these rules are so proper extension. These rules are kept in mind by doing this. So software will check for design rule, then electrical rule will check our proper connection is there, and then whatever circuit you have designed, the schematic is matching. And then there is antenna rule also in lower geometry, which is not mentioned here. It will check for antenna. There is no any antenna on gate is not formed because that can spoil the gate. So now we will go through quickly in how to do the layout for all these passive active components. Registers are widely used in analog designs, but the question is the tolerances of these resistors, they are very poor. Like resistance value can vary by as high as 20 to 30%. If you are making a resistor of 1000 ohm, it need not be 1000, it can be 700 or it can be 1200 also. So what you have to do, but matching the resistor is very good, in the sense if two resistors are placed close to each other, though you wanted in the design the resistor value to be 1000, but if it is 700, but both the resistor will be close to 700 only. This is what we mean batching, if they are placed close to each other. And by trimming of these thin films, you can make some resistor close to the value. But as a thumb rule, since absolute value of resistor can vary, so normally a ratioed resistors are used, like R1 by R2, and that will not vary much. So now you in a pure digital process, the value of the resistance, if it vary, doesn't matter. But for an active, but for an analog, the value of these resistors matter, and these resistor has to be linear also. So you can see this is a resistor which is made of N well. This is an N well. You make contact here, you make contact here. So one contact is here, one contact is here. This is the top view. So depending on this distance, the value of the resistors can be found. This is how it looks. So this is the complete well, blue. You make one contact, you make one contact. So now this will be L, this will be width. The current will flow from like this. Okay, so this will be what will the value of this resistor? There is a fixed resistance of these two contact. So this will come to R contact, and then since this is a diffusion, there will be some sheet resistivity which is RSH, then RSH into L divided by W. So this will come from R is equal to rho, that R is equal to rho L by A. So what is A? A is because this is the thing. So this is W, area of cross section, W into thickness. So that area of cross section will come. So based on this thing, you can see here. So R is equal to rho L over A, and rho over T we are defining at a sheet resistivity RSH, because that is not designer cannot change, it is fixed. Designer can only change L and W. Sheet resistivity is a property, it is a property of the process. So rho by T. So you have L and W, so you can adjust L and W. Sheet resistivities are given, so you can find this R. So normally if L and W are equal, so R is equal to R SH. So L and W are same mean square. That is why sheet sheet resistivity is given in terms of resistance per square. So that is the reason for this. So these are the, you can have a P resistor, poly resistor, N well resistor. N well, this is a well, you are making two contacts. P resistor, in a well you have a P diffusion. You can see this is a P diffusion, and you are making two contacts. Poly, you have a poly and you are making two contacts. So what is the difference if you see? Let us take this one. If you have an L, N here, P here, there will be some diode here, reverse biased PN junction. Okay, so because of this, there will be some depletion region also in the N. So N, this width will decrease because of the depletion region, depending on the voltage between across the two end of these resistors. So this resistor is not a linear resistor. There will be some voltage coefficient. So the value of the resistor depends on the voltage. Another thing is, since there is a PN junction reverse biased between this N well and P, there will be a current flow through this resistors. And third is, any noise at the substrate will be put inside the resistor, and any noise from the resistor can get transferred to the substrate, which can get transferred to other elements also. And you see here, if you see, what you do is, you have an N well here, this is an N well, you make an N well contact and you make some DC value, put some DC value, like it's an N well. So normally N well you put at a higher value, say 2 volt, you connect this. So now you have a 2 volt wall here. So this resistor is sitting here, so it is protected from interference of substrate now, because there is a two, you have shielded it just like a coaxial cable concept. So this is a shielded resistor, so you have protected this resistor. But again it will have some VCR because of depletion. Poly also have a poly depletion, but it is quite less. The VCR is very less, and this is a Fox field oxide, so the depletion will be very less. But the question is, if you have to carry a huge amount of current, this is a field oxide dielectric. This also is a field oxide dielectric. So this resistor is sandwiched between two dielectric. So heating properties, heat dissipation properties are too bad. So you cannot dissipate much of heat. Whereas well resistor, the complete well is there to dissipate heat. So each of these, in fact, there are some 5-6 positive, 5-6 disadvantages of using these resistors, and where one is to use, it depends. We will not go much detail in this. Now, you see, if you have to have a resistance of say 1000 ohm, sheet resistivity is say 10 ohms per square. So 1000 ohm means you divide 1000 by 10, so 100. You will have 100 squares. This means W by L will be 100. In one dimension, it is 1. On another, it is 100. So you cannot produce this big line where aspect ratio on one side, one dimension is 1, another 100. So it will be this line. It is not possible to produce. So what we have to do is we have to make it a serpentine. Yeah, like you cannot have long strips. So what you do, you have like this. If 100 means 1, 2, 3, 4, 5. So this is 20. So this width is 1. This is 20, 20, 20, 20. You have make it 100. You have make it serpentine like this. So effective resistance from this point will be now 1000 ohm only, from this point to this point. So now there is one way like this. Another way is you can have a sectioned here. What is the advantage? You have one segment 20, then you have a contact, then here you have a contact, then another. You have contacts here. You see which one is better. If we see from resistance point of view, this section is better. It will give you exact, because the reason is here you have corners. Where there are corners, they cannot be modeled properly. So here there is no corner. It's a line. It will have sheet resistivity. Then contact resistance of these two contacts will come, and they are connected with metal. Sheet resistivity is very small, whereas their corners are there. So this cannot be modeled. But only thing is, here it will take more area, since design rules will come for all these contacts. You cannot place this very close to each other because of design rules where this can be placed to each other. So it depends on your situation where you use what. Now capacitance are also quite commonly used. One of the simple capacitors is a MOS capacitor. You can see you connect source and drain together. This is one terminal, gate is another terminal, so it becomes a capacitor like this. But the behavior of this capacitor, depending on this voltage across the terminals, which is a gate to body voltage, will be like this. Okay, so you can use this. It's a non-linear first, as you are seeing this. So you can use in accumulation or depletion region. So it has a limited range. Or otherwise you can have a proper capacitance where with two metals or two poly and with an oxide, that also is possible to have. And you can have a poly capacitor or a metal nowadays MIM they call it, metal insulator metal capacitors are used. They are better than poly capacitors. This is how it will look. So this is the cross section, this is the top view. So you can see this is one plate, this is another plate. This is the top plate, this color is blue, this brownish is the bottom plate, bigger. We are taking contact at the top. This is the contact of lower plate, this is the contact of top plate. So capacitance will be this one. If you see here, So this is the bottom plate. This one, this if you see, which is brownish in color, this is the bottom plate, and these are the contact outside perimeter, right? And this blue is the top plate, and these crosses are the contact. So capacitance area, this much area, because the bottom plate is bigger, top plate is smaller, and the capacitance will be calculated area. Top plate will be calculated, and there will be some fringe capacitances. That way you have to model. There is a parasitic of bottom plate to substrate CB that will come. So some parasitic capacitance will come, which is 4 to 5% of this. Now this is a MOS transistor. So this is the layout, drain, source, gate. Okay, so you make these contacts of drain, source. This is poly, like this, and this is body. Now again, if you do the connects like this, okay, drain source you have put one contact, one contact. This is not proper. What is the reason? Because your drain area is this much. Okay, like there will be some diffusion in the resistance. This you have not taken into care. So this diffusion the resistance will come. So what you have to do is, if you put this one contact resistance, say 10 ohms, so you have put 3. So what will the contact resistance of 3 contacts? It will be 3 are coming in parallel. So you have reduced the contact resistance. Whereas if you do it here, there will be 10 of this contact, and this area will also lead to some resistance. So this resistance will directly come in drain or source. That will affect. Okay, diffusion resistance will come. So you can, this is a better layout. Now, same way, this is the W. You can see you should try to put as many contacts in the drain, as many contacts in the source, as many contacts in the body. The reason is you are decreasing the contact resistances, the parasitic ones. We will see again further. You see, if I am having a particular W and this is L, I have a very elongated resistance. So you can calculate these capacitances CSB and CDB. What will be CSB? This W and W into L. L is this much. Okay, so now, but you can split, say this W by L, it will have some ratio, you make it half. You do like this. So exact W you have make it half. So you have made 2 transistors connected in parallel. Overall W and L will be same, because this W, this will be W by 2, since you have connected in parallel. But now you see what is happening. Your CSB will reduce to half. How? Because you see, this is poly, this is drain source of one transistor, this is poly of second transistor, this is drain source of second transistor, and this source is being shared by these 2 transistors. So the capacitance will be W by 2 into L. So it is becoming half. Right. So you can see in the layout you have reduced one capacitance to half. Similarly, if you do, you have, but other capacitance dB is not changed, because drains you are seeing is twice here. But if you split in 1/3, if you make it W by 3, you can see CDB 2 by 3, and this also 2 by 3 you are able to do. So this you have to see how many fingers. This is known as a finger. So you are connecting these 3, or this. In circuit is same, but layout is different. It will make lot of improvement in the circuit performance. So this is how this layout is very, very important, how you have to do. Now matching means where, like a differential pair, each resistance, each particular geometry has to be matched. So then the precision of the device, where the devices are occurring in pair, that will change. So sometimes you have to use devices of different shape, and direction also has to be same. There may be use of dummy, and there is something known as a common centroid. So we will see those things. Let us see. One is interdigitated layout. It minimizes the effect of process variation. You see here I am having two resistors, A and B. Okay, so I have split A in how many parts? Three parts here. So one, two, three. So I have two options now. What I can do is I can put A1 here, A2 here, A3 here, B1, B2, B3, A1, A2, A3, B1, B2, B3, and you can join easily. But the question is, what happens if there is a process gradient from this end to this end? Since the A is coming first, it will see less process gradient, these three segments, and B is coming after that. All three segments will see huge process variance, right? Like this can be explained easily, very easily on the board. Now you are taking this resistor. So one, two, three. This is one resistor A. Another resistor you have placed here, which is A, which is B. See, if there is a process, normally in a wafer, when you manufacture, there can be some process gradient. Like if some we are doing some implant, some dopant. So dopant, if it is uniform, it does not matter. But if there is sometimes it is a gradient is there, right? So this means whatever you wanted to do a implant of 10, but there is a gradient, it is increasing linearly. Say, so here it is 10, 11, 12, 13. So normally 10, so 1 is extra, 2 is extra, 3 is extra. You can see here 1, 2, 3, 4, 5, 6. This will getting 3, 4, 5, 6. 6 is extra here for this, and this is getting 6, 5, 11 for 15 extra. Okay, so this value of this resistor will change much. But the advantage is connections, relative connections are very easy because they are sitting close to each other, you are able to make here. But the value of these resistor will vary. Another, if we do like this, now you see the effect. Now this 1, 2, 3, 4, 5, 6. You see this now it is getting equal. Whatever your gradient is there, they are getting equally distributed in this. But then what is that disadvantage? That how you connect these two. You will need, because finally these two you will have to connect here and here in one plane, and this also you will have to connect in another plane. You have to connect this to here in another. So the connections they become problematic, and there will be some parasitic because of these connections also they will affect. Okay, so this you have to keep in mind. Like this one, if there is a gradient, this resistor though you wanted R1 to be equal to R2, but here most of the gradient will, here it's more, here it's less. It has taken all the gradient here, so this resistor will be different. Here the gradient is uniformly distributed because this will be R1 plus delta and this also will be R2 plus same delta. In this case, it is R1 plus delta and this is R2 plus some 3 delta. So this kind of differences will be there. But here connections are becoming more difficult. So you can see here you can go 1, 2, 3, 4, 5, like 6 here, and this is 15 here, 6 and 15. You see here 1, 2, 3, 4, 5, 6. So you can see 1, 3, 4. This is 9, and then 6, 4, 10, 12. So 9 and 12. So that way you are able to you are able to reduce the variations. Okay, so there are many different techniques. So this is known as the interdigital. So sometimes you have to use an interdigital resistors. And another thing is, which is important, is you see here. You see there is something known as a neighborhood effect. You see this B is surrounded by two A's. This A is surrounded by two B. When you do the etching of in this area and this area, this area will be uniform. So this means this width will be same. It will not be over etched, it will not be under etched. Right? But if you see this A, here it's an open. Okay, so since they're open, there can be more etching, over etching. So this width of this A will become less, and this B also become less. So what we have to do? So we have to see that the surroundings are same. So I put another block here, which is a dummy. Okay, it is not adding here. Also we have put dummy. So now this whole thing is completely matched with each other. So they have the same environment. This is known as a proximity effect, because here B is seeing here some structure uniform, but this A on one end it's seeing B, on other end there's nothing. So I have to put a dummy here. So there, because of then all these resistor segments they are seeing the same environment. So that is important. In any layout, axis of symmetry is important. Axis of symmetry can be in X and Y. So it should be symmetrical. You can see here, you can place this AB in different ways. Like these two resistors are there, A and B, which are equal. I can place it like this. So now it's a symmetrical layout across this axis. Right? So this X and Y both are symmetrical. Now you see if the variation here, again it's a linear variation, 1, 2, 3 and 4. So what will the variation in A? 1 and 4 is 5 and 2 and 3 is 5. So both will vary same. So value of both A and B will be same if they are symmetric. This is interdigital. AB. Here it will not be same. You can see 1, 2 and 3. 3 and 1, 4. 1 is 4 and 1 is 6. But it has some, you can see axis of symmetry is different here. So variation is not same. This is again it's symmetric. So but here value of A resistance is twice the big than B. Now there so there is something known as these resistors where you do the axis of symmetry. That layout is known as a common centroid layout. So there are 4 rules of doing a common centroid. One is their coincidence. This means the centroids of the matched devices should coincide at least approximately. So coincide means like this one. Here the coincide of B and A, they are both matching. You see the axis of symmetry of B is also this line, of A is also this line. It is matching in X and it is matching in B also. But here it is not matching. Axis of symmetry of A is this, axis of symmetry of B is this. So they are not matching. They are not coming on the same line. Okay, so this is axis of, so the symmetry should match, the coincidence should coincide, and then their dispersion and compactness. One is dispersion, like here dispersion is not there. You can see BB are close to A is dispersed, but B is there very close. This is dispersed. Okay, they should be spread out. And another is it should be compact. Layout has to be very compact, normally a squarish. You will not go for, aspect ratio should be 1:1. That so ideally should be square. You have to try for this. So this is a common centroid layout. You can see if A and 2, there are 2 resistors. both value of same, you can place like this: a here, b here, rather than placing a here and b here. You have to place this way, so this is better. Okay, now if you again, you can make more fingers. You have, then you can place like this. You have put a here and a here, b here and b here. So you can see here common centroid is matching, dispersion is also there, it is dispersed, and so gradient is also spread across all these segments. So sometimes you have to use a shield. So this is a shield, is very clear. You have put a shield, and this shield has to be connected to a particular voltage. So this is used in RF designs. Then you see in a circuit there may be some device which is consumes lot of power. So this is a power device. Now the power, the thermal contours, this device is generating power. So these are square, these circles you are seeing, these are the thermal contours. Now if A and B resistors, alignment is also important. You are placing A and B like this, and you are placing A and B like this. So are they both equivalent, or which one is better? So you see here, the B is seeing this thermal contour, means this circle, all points on this circle will be at one temperature, all points on this circle will be at different temperature. So B will be at one temperature, A will be at another temperature, and resistance varies with temperature. Okay, so the value of A and B will vary, though you wanted the same value for A and B, but because of temperature, the value is varying. But if you align like this, then both A and B variation will be same. Okay, so this is not correct, and this is the correct way of doing a layout. Now both integrated and common centroid also you can use. So you can see this, you can spread out between this. D is a dummy, so outer ring is all dummy, and you can see how 4 segments, 16, how you are spreading out A and B. So when the segments are more, the layout is also becoming more and more complex. Now this is a differential pair, so you can have like this AA BB AA BB or A BB A, like this. So these are the various, process variation can be averaged. It is a good matching, you can split them in various fingers. Okay, so you can see yourself now on an XY we have separated D and B here, D and B here, this is D and A, like this, and or we have made like axis of symmetry common here. So again, you have to put these dummy devices, these dummy transistors are put for a proximity effect, and these dummy transistors, they are not connected to any voltages, they are just dumbing, they will be floating, whereas these are the real transistors, so these are the dummy ones. So now if you see, if you are giving a, this is a transistor, you are connecting some voltage here. So why this is wrong, why this is correct? Because if your voltage here is 1, this is a metal line, but metal will have some resistance. So this part will, if this is 1, this will get 1, but this will not get 1. There will be some drop across this. Okay, so this drop will be more here. But if you connect 1 here, this segment and this segment will have the same drop. So this is matched. You can see axis of symmetry is there. This is axis of symmetry. Here there is no axis of symmetry. So axis of symmetry is very important in these. So matching may occur because of these: oxide damage, impurities, bias, temperature, etching. All these things can happen. And it may, the absolute value of any component may vary. So you have to match these components to nullify the effect. So these are some of the techniques. Use transistors with the same orientation. So minimize the contact area by stacking transistors. It has to be symmetric and shielded guard rings, and these are the common things you have to do. You should always have a multi-finger transistor. You should never have like this is a multi-finger transistors. So in a multi-finger transistor, the rule is the width of each finger's gate resistance of the finger is less than 1 by Gn. So based on this, for low application, 1 by 10 is fine. So this is a thumb rule by you have to generate of this multi-finger capacitance you can calculate. And if this is W by 5, so this is a formula you can calculate. So in a multi-finger, you can optimize the number of fingers so that the parasitics are minimized. So you can see this is a differential pair. You can like this or like this. Okay, so now the way asymmetries may lead to mismatch, introducing input referred offsets. And if you have to suppress these noise and non-linearities, so C and D you can see here, this is a symmetric layout. This is not a symmetric layout. This also is a symmetric layout. So it will even out the noise and non-linearities. Now there is a effect of a gate shadowing. Now if you do this source drain implant, you see the source drain implant is a tilted implant. It is normally tilted by around 5 to 8 9 degrees because of channeling effects. But tilted implant has disadvantage because of shadowing. You see this region here, you will not get any implant. That is the shadowing. So there will be some asymmetry in this region. Okay, so then you have to layout in a correspond like this. If you do a layout like this, so here the asymmetry will be in both the drain and source, whereas in this case the asymmetry is towards this region only and not towards this region. So here you have made both drain and source symmetric. So that is the advantage. So you can see the asymmetry can be emulated by adding dummy, and you are putting some dummy transistors also here. So this is a common centroid configuration. This is a common centroid. As I told you, if there is a gradient, so if you place the transistor in this, the gradient will be divided across these transistors. And cross coupling. Now when you connect the transistor, there will be some cross coupling effects. Like this transistor you have to connect with this. This you have to connect with this. So you can calculate these cross coupling effects. But this approach, you are able to filter the gradients, but some other effects are added. But overall it gives you a proper matching rather than putting in all the fingers close to each other. Now there are certain shallow trench isolation rules also, because nowadays these transistors, they are separated not by a field of sight, but there is a shallow trench isolation. And so you have to insert dummy fingers, because otherwise there will be a trench across these. So you have to like these two, we have to there is one gate, we are putting a dummy gate here, and this gate is grounded, as you can see here. Okay, it is like this. So this is a properly, it has been done like this. So this also you are putting a dummy here and here also. So similarly with the well proximity effect. So this your implant, they are getting scattered here. So that will also affect at this particular border. So again you have to put a dummy here to alleviate this problem. So all these then interconnect capacitance, these fringe capacitances will come, and you have to see, you have to adjust these capacitances. Then there's a latch up issue, because BJT is formed at one end, and you have to suppress that BJT. What you have to do, you see, if you can, there is a CMOS structure, NMOS, PMOS, and Q2 and Q1. These two transistors BJT are formed. They are interconnected in such a manner. If this transistor is on, what happens is you raise slight a small voltage here at X point. What happens is IB will increase, this transistor will become on. So it will start drawing current here. Right. So IC will, if there is a small IB, huge IC will come. And some of this IC will go in as an IB of this. It will turn on this. So this IB, huge IC will come here. And this IC, some of this IC will go in this IB also. It will further increase this IB. This IB increases, IC will increase beta times IB. So this, so you can see here, then a stage comes, a lot of current flows from VDD to ground. So that is a latch up. So for this you have to minimize this R2 and R1, because if the node potential at node becomes 200 or 150 millivolt, V base to emitter voltage should be 200 250 millivolt. Immediately this Q2 will on. Similarly, this voltage, this is a PNP. So this voltage, your emitter to base voltage should be more than 200. So how you can reduce this voltage? By reducing this resistance. So this contact R2 and R1, substrate and well contact, you have to reduce. You can eliminate. Normally, if your gate is long, connected to metal, long metal, then metal act as an antenna. And while doing CMP and etching is a dry etching, dry reactive ion. It's a reactive ion etching, so it can destroy the gate. So what you have to do is you have to cut this metal short. There is a rule, you cannot have this metal more than a particular limit. So you are cutting this metal here and splitting between M1 and M2. You can see here M1 and M2. So these, then you have to, the sensitive circuits has to be surrounded by guard rings, as it is seen here. Guard rings needs to be connected to different voltages. Okay, so these are some of the guidelines for noise minimization. You have to maximize separation between digital and analog bias lines to be separate. Guard rings for isolation. Multiple supply pins you choose. You choose wells for isolation, shielding. Use bypass capacitors. Use metal lines with constant bias and things like that. So all these things you have to, and various blocks you have to place. If LNA is a very sensitive block, DA and is a very sensitive, is a very high speed block, these two blocks should be further apart from each other. Don't put these two blocks close to each other. So in a layout where the circuit is complex, how to place these components, which is known as a floor plan, that also is very, very important. That will decide the overall behavior of the circuit. Now I will show you some of these layouts which we have done, taking care all these things. You can see some of these layout. This is a 24-bit ADC, this particular thing. So it's a 24-bit sigma delta ADC. So you can see here, this is the digital part. Or if I will try to, what is ready, increase the size so that you are able to, I think now it should be clear. So it's a 24-bit sigma delta. Now this is the digital portion, and this is the capacitor array, this greenish. This is a bypass capacitor. There is one LDO also. This is one LDO, voltage regulator. So this is a bypass capacitor, green. And this is it's a two-stage modulator. This is the first stage, this is second stage, this is voltage references. These are the capacitor arrays. So there are around 128 bank of capacitors, so this violet color, and these are the pads. So this whole thing is this dimension is 2 mm only, and by 2 mm. So this is how it looks, some of these layouts. And these are a different now I will show you this. So this is again, it's a voltage regulator, and this is a power MOS. It gives 150 milliampere of current, this one. And so it's a one transistor but multiple fingers, there are many fingers, so that it is able to give 150 milliampere of current. So this is again, this is a single power MOS which can give 3 ampere. You can see that there are multiple fingers, and the challenge is to lay out these fingers so that all fingers, they should conduct same current, because if one finger or few fingers connect more current, then they will finally burn out. So current has to be divided equally amongst all fingers. So similarly, this is an LVS driver. It's a quad. There is a 4. If I increase this, so there are 4 segment, 4 LVDS are put in one chip. This is 1, this is 2, this is 3, this is 4. So you are seeing more or less it is symmetric, and all these 4 LVDS are put so that there is no interference between amongst these 4 blocks between them. So this is your 485. This is your 488. This is a transceiver. This is how it looks. This is 422. So this is a C2V. So this is the digital part, and this bluish is again a capacitor array. You can see this is the power ring for a digital part. This thing is a power supplies, power and ground for digital, and this is a power and supply for analog. So you can clearly see how they are separated. And power grid, VDD and VSS for analog, and for a digital they are separated. Areas are also separated so that they should not interfere with each other. So these is a clock high voltage drivers, and you can also see here these are various op-amps here put, and drivers, which is a last stage. Here criticality is they have to drive the very high load 30,000 puff, and the speed should be 10 megahertz, and the voltage levels are also very high. You can see -5 to 3 volt input and 5 volt to 15 volt output level. So switches are also high, they should be able to drive high currents. So these are some of the, this is again a power MOS. This a single transistor, it can give 3 ampere. So there are many fingers in this, 15 points. They are distributed for current monitoring, and the temperature. There are in this device there are 15 temperature sensors, because you which are put up, which are set up across various points in this circuit, so that the temperature of each area is monitored, and where the temperature is shooting up, you have to take preventive measures for that, so that the device doesn't burn. So these are the some different types of inductors which we have been made in different shapes. So these inductors are made by metal, some polygonal, some squarish, and different shapes. These things have been made. This is in fact, this is one circuit which is an APS, active pixel sensor, which is a camera, basically CMOS camera. So this array which is not shown here, it is this is a photodiode here. It's a PN, and this is, there are 320 DACs ADCs which are placed here, the 12-bit ADCs, and dual slope these all. So total, because this dimension is 320, this dimension, it's an array of 256 cross 320. So 320 DACs have been ADCs have been put here. So this placement is very important in a circuit. So this is a 16 This is a controller. It has a 16-bit microprocessor in this, and this also is a controller. It has a 16-bit microprocessor, and it is a radiation hardened. And this is a baseband. This is a GPS receiver, which is an GPS receiver. It has a 32-bit processor, Leon processor. So the chip area, as you can see here, is 11 mm by 11 mm. It has 4 million gate. 4 million gate into, you can multiply by 4. So 16 million transistor this particular is having. It has the 32-bit processor, and there are several peripherals and some memories are also there in this. And so these are some of the designs which academic institutions we have fabricated. They have designed NIT, IASC Bangalore, IIT Kharagpur, then Nirma University. So some of these designs we have fabricated for them. This I'm showing you some of those designs. These So as an overview, let's go to the previous. So I've shown you some of these. Some of these designs. So now we have covered starting from the design. So we have to do the front end part. We have to finalize the architecture, and then do front end simulations. And if the specifications are met, then we have to go for a layout. We have to do the layout, then do the PEX part. And if the PEX is also meeting the specification, then we have to do the complete taking into consideration the RLC part. We have to do the complete simulate the circuit for various parameters, and then we have to release GDS. If it doesn't work, then you have to change either the layout or you change your architecture so that this particular thing is able to work. So this is the complete flow for an analog. And as I told you, in an analog there are various modules, and if you have to learn this complete analog design, so the starting point is very the various blocks I had shown here. So you have to take up each block by block, and you have to go through it solving their these. So this, like common source, which is a voltage to current conversion, then common drain, voltage to current, simplest voltage follower, common gate, and basically all these controlled sources. So current controlled common source, and common drain, common gate, then diode connect transfer, active loads, then a cascade, then a folded cascade. Then comes your differential amplifier, then cascaded differential amplifier, then current mirrors, how to make current mirrors, and then your how to make a cascade current mirror, what is the advantage of a cascade, how to increase the output, how to make high output impedance, how to do matching, how to do current multiplication. So these things one by one you have to take up, and you have to understand the what is the large signal model, what is the small signal, how to derive parameters, various parameters, like your dynamic range, your output swings, your frequency response, your poles and zeros, and biases, how to noise, how to connect the noise, and from the front end part, and after doing the layout, the simulation part. So then only you will be able to realize these circuits. And basic building block is an op amp, and once you are able to do the op amp, and you see, another thing is here, there is something, and whenever you start design, there is something known as a design kit process design kit. I will there are some 10-15 minutes I will cover. So what is the meaning of a process design kit? So process design kit is a collection of files which will help you the custom, which will help the circuit designer to be able to design circuits. So what these design kit includes? These design kit includes what are the components, active and passive, what are their names, what are their symbols, what are the models, and how to make the layout for these, and what are the design rules, what is the LVS, what are the technology files, what is the parasitic for each layer, how to extract, and scripts. So all these data they are included. So normally the foundries, fabrication, manufacturing plants like TSMC or UMC. So these foundries they prepare this PDK and they give to the design houses, and design houses uses this PDK to design their circuits. And so PDKs are made for the designers. It has PDK specific for an even a design flow on a particular design tool, like whether you are using SNOPSIS or a Cadence. So your technology files have to be compatible with those design tools. And now, since the transistor sizes are falling, and when the your mismatch becomes more, on-chip variation also increases, and with this the yield suffers. And nowadays people talk about design for manufacturability, design for yield. So what are those issues? Though some of those issues are also highlighted in these PDKs, how to enhance the yield. So I will give you one example. You see, this is a band gap circuit, band gap reference. It's a voltage reference. This is a schematic. Okay, so what the PDK will do is, like, in this is a circuit. So you should be able to simulate this circuit. Now you have simulated and you have seen this references, how much variation per temperature it is coming. And based on the P cells, now this is a transistor, this is a transistor, this is some resistor. So based, this transistor finally has to be laid out. So you call the P cell, and P cell will lay out this particular transistor, and you call this element for P cell. For this element they will do all these layers for this, like as shown in this figure, and it will interconnect. So you get a complete physical design of this, and you can simulate this physical design to make. After now, this simulation will takes into care of parasitic elements also, whereas if you simulate using this circuit, it doesn't take into care the physical part. So all these things are possible by using an integrated analog design flow. So technology file means what are the different layers, what are their names, how many vias, how many metals, what is the stream in, what is, because in a layout normally each layer is represented by a color. So what is that color for each layout? So those things are there. And P cell is known as a primitive. It's a parameterized cell. It will have the information about the symbols. It will have a CDF, and it will have entire information about the length, width, electrical information like what is the capacitance, what is the resistance, and some logical information, terminals, how to connect the terminals for a transistor, also for an active component also, and for a passive component also. Because to aid the designer, otherwise the designer has to lay out all those layers himself. And if he calls, like for a transistor, so you have to make a transistor of 4 by 1 W by L, then you call this P cell for that particular transistor, it will place those layers automatically. And contacts, it will give you the contacts there on the transistor, and you can interconnect those contacts. So these P cell library use, it has all device characteristics. Device characteristics means about the geometry of the device, about the voltage behavior, about the spice netlist. All information of the device is there in the P cell. And So this way it helps you. So this is a symbol of a transistor. So you will have these CDS term D, G, S, and there will be some parameters here. So this is how it is represented, and a layout parametric scale will, like you can see this, all various layer, various instances they are put. It will give you a layout of a transistor like this, where it is showing two contacts here, 1 and 2 here. So all these layers are active area, your diffusion, your poly, your contact, your metal, your via, it will be there in this. And it can calculate the when you connect the parasitics, when you connect the two transistor, you have to calculate the parasitic of the interconnect and take into consideration. So that is a schematic driven layout, where from the flow you have made a circuit, and your schematic is formed based on the your layout is formed based on the schematic. So your circuit drives the schematic. So schematic driven layout, you have design specification, you have made the circuit, and finally you have simulated it, and after simulation you find it is meeting the specification, and then you can finally have a schematic driven layout. So it will use the P cell, it will make the complete layout and give it to you. You have to interconnect various elements, extract the parameter, resimulate, and then do the post layout simulation as shown here. And then finally, so this is the a summary of the design development kit. So these are the layers, like of a particular UMC fab, UMC foundry, like WP means P well, N well. This is layer number. This is the abbreviation. GC means gate contact. This is active. This XP means P diffusion, N diffusion. CS means contact. This is a gate poly. M1 is metal. This is the number, and the color is also there, which is not shown here. V2 is second via, M2 is second layer. These are the layers. So you can see here, for an analog design, what you need is, you need a model file. Model file is a spice parameter. You need a P cell, which is gives you all the layer information for placement, and you need some IO libraries and the technology files, like this files. What are the various layers? You can design the circuit. And for a digital, you need the lookup table and the Verilog models for making, and the technology file for doing the synthesis and doing the APR. You need a standard cell library, where like in UMC at more than 560 standard cells. So these standard cells, Verilog models will be used to synthesize the circuit, and they will give a complete form, and then TLU, this is a lookup table, will be used to evaluate the parasitic. Then IO for IO pads, and finally you can close this. So this is how, in a brief, today we discussed the front end part, how to make the, how to realize a circuit, how to do the biasing, how to adjust W and L, and we discuss some of the issues pertaining to the layout. In the next, we will take one example. We will take an A to D converter, how to design an A to D converter, and what are the various steps, what are the issues. So the next lecture will be on A to D, which will be held tomorrow. And now, if there are any questions on whatever we have covered today, you can please ask.